Welcome to part 3 of the video series, Linear Regression, a Linear Algebra Perspective. Today we are going to discuss linear independence and also fill in some gaps in concepts we have discussed in previous videos. So let's start off. We are first going to discuss the answer to a question I left off with in the previous video. So let me lay the base a little bit. Last time we discussed the concept of a column space. And we had said that if all the columns of this matrix, say I've written down the same equation as in the last video. So let's say this is column 1, this is column 2, and this is column 3. Then every form, every vector that you can get by linearly combining these three columns. So linearly combining means you add a scalar in front of each column. So let's call it S1C1 plus S2C2 plus S3C3. So every combination of these three columns gives you the column space of the matrix, and let's call this matrix A. Yeah. Now the next thing we had said was that this matrix, if you notice this equation, it has four mini equations, right? Because if you notice there are four rows over here. So four equations, but only three variables. Now, in this sort of a case, you may not get a solution for x1, x2, x3. There may not be values for x1, x2, x3 such that all four equations are satisfied. However, there are situations where there could be a solution. So the question was, for what values of b1, b2, and b3, or for what value of the vector b, can all these equations be solved? Let me give you the answer for that. The answer is that b should be a part of the column space of A. Now, this may not be fully clear right now, but it will start making more sense while actually discussing the regression line using linear algebra. This is just a sneak peek for you on what's about to come. Okay, so that was the first thing I wanted to discuss with you all. And the second thing is this, that if you recall in the first part of the video series, I had said that let's say there are two column vectors. Let's say there's V, which is equal to V1, V2. And these are its components. Let's call the components instead of X and Y. Let's just say this is X1 and this is X2. Just so that it corroborates with the components we've written over here, the variables we've written over here. Okay. And let's say there's another vector called W, which is equal to W1, W2. And similarly, W1 is the X1 component, W2 is the X2 component. Okay. Now, the thing we discussed was this, that if you want to join these two column vectors and represent them together, you could do that using a matrix in this form. Just put the columns one by one together, right? And similarly, the transpose of the matrix, remember the variable's name is M, okay? You could use A, you could use B, you could use anything, would be V1, V2, W1, W2. So if you notice over here in M transpose, the components of a single vector horizontally put or in the form of a row vector. We see the same thing happening over here even with A. So if you see 2, 4, 6 are the components x1, y1, x1, x2, x3, but they're horizontally put instead of vertically put. Yet we call this matrix A instead of A transpose. It is fine if you even say that that equation is A transpose instead of A. But saying A transpose may become more complicated in concepts that we're going to discuss later. That's why we just simply call it A instead of A transpose. There is nothing wrong in this. These are just different ways of representing the same thing. As I told you initially, that it is just convention that you represent vectors as column vectors, and therefore when you join them, you could say you've joined the columns together. Okay. Alternatively, you can always use row vectors and make that A. There is no issue between the two. When we talk about equations, we are going to try and use A, but I'll inform you about it whenever we work on any concept in the future. Okay? That's the second thing that I wanted to discuss. Now let's move on to the main topic for today, which is linear independence. Another really interesting topic, and we're going to use the same equation to help us out in that topic. So have a look at this. Okay. Now in the previous video, I had said that the first column, second column, and third column can actually be combined. Okay. So what I mean to say is this, that C1 plus C2 is equal to C3, correct? Now what I'm going to do is I'm going to get C3 to the left hand side and write it as a linear combination. So let's say C1 plus C2 plus minus 1 times C3. Okay. And what would this be equal to? 0, right? So I'm going to write the 0 vector in the form of a 4-dimensional vector because C1, C2, and C3 are also 4-dimensional. Okay. Now the thing to note over here is this, that if the columns of a matrix can be linearly combined to give you the 0 vector, then the sequence of column vectors are linearly dependent on each other. So all three of them together are linearly dependent on each other. Okay, linearly dependent. Now, the interesting thing comes over here. When do you say something is linearly independent? So let's say C1, C2, and C3 could not be linearly combined to give you the 0 vector. Then you'd say that they're linearly independent of each other. The only thing is this, that C1, C2, and C3 can give you the 0 vector while being linearly independent if each of the scalars is equal to 0. So for example, let's say C3 was not equal to 6, 4, 10, 8. Instead, it was equal to 1, 7, 15, 2. Now you'll notice that there is no way of combining the three columns this time to get the 0 vector. So therefore, you could say that the only way the 0 vector could be found is if you did this, 0 times C1 plus 0 times C2 plus 0 times C3. That's the only way you'd get the 0 vector. Okay, and this is the definition of linear independence. That given a sequence of many vectors, so let's say you were given a sequence of vectors v1, v2 up till vn. If the only way they gave you the 0 vector was by doing this, 0 times v1 plus 0 times v2, so on, plus 0 times vn, only then are they linearly independent. Another thing to note over here is this, that these vectors, sequence of vectors, could be anything. It's not necessary that they are columns of a matrix. They could be any set of vectors. Okay, so they are linearly independent only in this case. This is the only case in which they should combine and give you 0. Okay. Now there are two interesting things to talk about. So we said that C1, C2, and C3 are together linearly dependent on each other. But what if I only talked about C1 and C2? Are C1 and C2 linearly dependent on each other? No. Okay. So C1 and C2 are linearly independent of each other, right? Now, when you have two linearly independent vectors, and when they are linearly combined to form every single vector possible, they'll give you a plane. This is something I mentioned briefly even last time. Now, a little bit on why it's a plane. Let's think of the xy plane, easiest example to give you. So in the xy plane, if you think of it, okay, x could be represented as 1, 0, and y could be represented as 0, 1. Okay. Now, x and y, just x and y, can be used to represent every single point on the plane. Every point, right? Even if you used an extra axis, it would not be of any use because even the extra axis would be in the form of x and y. Okay. Now, it is also so that you can't even just use one of these two axes, because let's say you just used x, then you'd only be able to represent the horizontal points, right? But you wouldn't be able to represent the vertical movement or the vertical positions. So therefore, we could say that a plane does require two linearly independent axes, because only then can you get every single vector in the vector space. Every single vector on that plane, you would require those two axes, linearly independent axes. There is one more point over here. It is not necessary that C1 and C2 or any two linearly independent vectors are perpendicular to each other. So here we saw that x and y were perpendicular to each other and they were giving you every single point in the plane. But it's not necessary, which is a very interesting thing to remember and very important thing to remember, that C1 and C2 may not be perpendicular. And this is the case for every single linearly independent pair of vectors. Okay. Now, what does this mean? Let me tell it to you with an example. So let's say you had a vector v, and you had a vector w. Okay. The only way these two vectors, and let's say they're both two-dimensional vectors, okay? The only way these two vectors could be dependent on each other is if one was a multiple of the other. For example, let's say if v was 1, 2 and w was 2, 4. That's the only way they can be dependent on each other, right? Because here, if you notice, we don't have a third vector which can be added with another vector to give you another vector, right? The only way that they can be dependent is through being a multiple of each other. This is where the interesting part comes. This means that if you remember in part 1, we had said that anything that is a multiple of a vector, so when it's, multiplied by a scalar, it lies on the same line. So 1, 2 and 2, 4 lie on the same line. This means that any vector that does not lie on the same line as another vector within a plane would be linearly independent from that vector, right? And this is where the interesting part comes. It means that, let me represent it. If this was your x-axis, you could have another vector going this way, 45 degrees to it. Let's call it z dash, okay? And it would still be linearly independent of x. Because here linear independence is not the same as independence in geometry. In geometry, we've read about, components being cos component and the sine component. That is not the case over here. This is a very linear algebra way of thinking of it and not a trigonometry or geometrical way of thinking of it. Extra video on using axes that are not perpendicular to each other is in the process of being made. We will dive deeper into this thought in that video. For now, we'll end this video over here just by giving you a small introduction on what linear independence means. And next time we'll use the same information to talk about other topics that will help us out in finding the regression line eventually. So hope you have a great week ahead and bye-bye. Thank you.